we have come to experience 4 modern atomic theory, which means that we're going to refine our model a little bit further. And maybe the model of the atom we have now is kind of what you're familiar with. The nucleus is great. I have no problems with the nucleus. It's got the protons and the neutrons. When we left off with the Bohr model, we've got these electrons, and it almost seems as though they like fly around the nucleus in these rings or shells. And when you kind of think about it, that model doesn't support the fact that atoms have to be 3-dimensional, right? And matter is 3-dimensional. So we need to clean up the electron structure a little bit to provide for a 3-dimensional model of the atom. And really the nucleus then is like a marble in the middle of a giant stadium, like a football stadium. And so we need to prove that the bleachers and the stands are really 3-dimensional. Electrons can fly not just in a ring around the nucleus, but really in all dimensions around the nucleus. And so our modern model of the atom is really credited to some of the work of Erwin Schrödinger. And he was really a mathematician that did some crazy mathematics that we do not need to get into, but came up with what we call the quantum mechanical model. And here's the big difference, that the quantum mechanical model doesn't specify an exact path for moving electrons around the nucleus. In our previous model, maybe we thought, oh, make it a little skinnier. We've got the nucleus in the middle, and there's the protons and the neutrons, but then we have like these rings. And some people think that these electrons just like fly around the nucleus in this ring. And now we're going to say that this new quantum mechanical model doesn't show an exact path that the electrons follow around the nucleus. Instead, we're going to try to define it as a 3-dimensional space. We're going to call it an orbital. It's a 3-dimensional space around the nucleus where we have a high probability of finding an electron. But within this space, the electron is somewhat free to move on its own, and we may never know the exact location of the electron, but that we have a high probability of finding it in this location, at this distance from the nucleus. And so they're trying to maybe compare an atomic orbital to like the wings of a flying hummingbird. That if I'm just watching a hummingbird, I kind of see this blurry region where I know the wing is somewhere in here, but it's constantly moving. And electrons are constantly moving. And so I don't know exactly where the wing is. If I had a way of taking a snapshot, I could freeze the bird in time, like not harming the bird, obviously. Maybe the wing is up on the top. Maybe the wing is on the bottom. Maybe it's in the middle. But it's moving so fast that when I just look at it, I see this region where, the wing is somewhere in here, but it's constantly flapping. And so we kind of think about the atom in a similar sense, in that we've got the nucleus, protons, neutrons, fantastic. But this electron cloud is really just a region where we have a high probability of finding an electron. And these little blue dots around the nucleus aren't like showing that there's billions and billions of electrons. It's just supposed to show that where this light blue color is darkest is where we have the best probability of finding an electron. And as we get out to the edges of this electron cloud, where there's less dot density or less electron density, we just have a lesser chance of finding an electron in that region. And so this whole region might be considered an orbital. Okay, now it's going to get crazy, but stick with me, and I think we can do this. Okay, so some people call this the shell model. I don't know. I just refer to this all as little orbitals. We're going to look at different types of orbitals and the fact that they have different shapes and sizes and energy levels. Oh my gosh, they did not teach me this in my last science class. Yeah, it's because now you are ready. Your minds have matured and you're ready for something super wacky, but kind of cool. Okay, so the shell model of the atom is a simplified version of this quantum mechanical model that has lots of crazy mathematics and probability, and we're going to try to boil that down and make it manageable and understandable. It describes the main electron energy levels, and they're called principal energy levels, and some people still call them shells, but I do call these energy levels. And each principal energy level has a different number of sub-levels or subshells, but I call these orbitals. So each principal energy level has a different number of subshells. I'm going to say a different number of orbitals. Subshells are fine, but I'm going to say that the energy levels contain different amounts of orbitals. Okay, so in this crazy picture here, in pink, it's showing the energy shells, or you are totally cool if you want to call them energy levels. I'm going to call them energy levels. Sometimes they're called principal energy levels or principal energy shells. But this kind of follows the Bohr model a little bit in that energy level 1 is the energy level closest to the nucleus. And if it's close to the nucleus, it's low energy and it's small. I mean, if you look at energy level 1 as a kind of a circle, it's the smallest energy level. So these electrons can move, but they're not moving in like a large distance from the nucleus. If an electron is in energy level 1, it's pretty close to the nucleus and it's low energy. As we move away from the nucleus, from energy level 1 to energy level 4, and there are up to 7 energy levels occupied by electrons in elements that we know of today. I mean, energy level 4 is bigger, it's farther from the nucleus, it's higher in energy. So I know that if I have an electron out in energy level 4, on average, it's farther from the nucleus, and there's a lot more space then for this electron to move. Higher energy, bigger distance from the nucleus. It's just a bigger energy level. All right, cool. So then in yellow, they talk about the number of electrons that each energy shell or energy level can hold. Ignore this thing for now. We've got a better way of figuring out how many maximum electrons can be held by each energy level. But you may have heard this in a former life, that the first energy level can hold 2 electrons, the second holds 8, the third holds 18, the fourth holds 32, and so on. Oh my gosh, do I need to memorize this? Absolutely not. There's a fantastic way of us understanding why the first energy level can only hold 2 electrons and why the second can hold 8. Seems kind of random, like where do these numbers come from? What did it say, like 2n squared or whatever? Well, if I look at this number 25, this question 25, science and engineering practice using models. Here it says, why does the number of electrons in each principal energy shell or energy level, why does the number of electrons increase as the number of the shell increases? And whenever they say shell, I'm really thinking of it as an energy level. You can call it a shell, I'll know what you mean. But they're basically asking us to look at this pink part of the model and the yellow part of the model. And so why, as I move further away from the nucleus, why as the energy level increases, can the levels hold more and more electrons? And maybe you just kind of said, well, I don't know, because they're bigger? And if you did, you'd be right. The energy levels are larger and have room for more electrons. On average, like in the fourth energy level, it's a really big region around the nucleus. So yeah, it just makes sense then that it could hold more electrons than maybe the first energy level, which is a small region really close to the nucleus. All right, so that kind of makes sense, right? So far, okay? Now we move on to this blue part, subshells. I call subshells orbitals. Orbitals come in different shapes and different sizes and different energy levels. They have letters that indicate like the size and the shape of the orbital. The letters for these orbitals are S, P, D, and F. Oh brother, why did they pick those letters? Well, some of them make sense, but some of them are kind of arbitrary. Each subshell or each orbital has one or more orbitals shown by a box. Okay, so I'm going to say it this way. When they give you these pictures that have like this SPDF stuff, where right now you're like, what is going on? Every box represents a specific orbital. And each orbital can hold 2 electrons. And so eventually what we're going to do is look at these boxes as a model of all the different orbitals that are available in an atom. And each box or each orbital can hold up to 2 electrons. It can hold 1 or 2, 2 of them max. And we're going to show the electrons with arrows. That eventually I'm going to fill these boxes with electrons, and I'm going to fill them with arrows to show that electrons in a box are charged. I mean, obviously electrons are these negative particles, and they're constantly moving. And when they move, they create like a little magnetic field around them. But if you have 2 electrons that are together in the same orbital, they always spin in opposite directions. So the box is an orbital, and the arrows show that electrons have 2 electrons, and they must spin opposite. And it's just because you have these moving charged particles. And I mean, last time I checked, electrons were both negative, and like charges repel. Well, they can't just like totally fly out of the orbital, but they'll create these opposite, like electric fields almost, magnetic fields, where they'll spin in opposite directions to help accommodate some of that repulsion. Okay, so I'm not concerned about this information in blue a whole lot yet. Instead, I want to move on a bit, and I want to look at this more visually. Okay, so here's a good picture of the orbitals. We can come back to the blue stuff later. All right, so look at these orbitals. They're like different shapes and sizes, and they're like little bubbly regions around the nucleus. That's kind of where I want to start. It says that atomic orbitals in an atom are denoted with letters S, P, D, and F. Each shell has 1 s orbital. And by saying each shell, it kind of means like each energy level. Okay, so let's look at the s orbital. S stands for sphere-shaped. The s orbital is spherical. It's like a little spherical region around the nucleus where you have a high probability of finding an electron. Up to 2 electrons to be precise. All energy levels have an s orbital. So let's say this is an electron in the first energy level. So I'm going to say 1. And then the shape of the orbital is a letter. So we start to put these symbols together to try and locate an electron or describe the location of an electron. So it's in the first energy level, and then I might say it's an s orbital. And I would be describing a region like this little orange space, this small spherical region, three-dimensional, around the nucleus where I have a high probability of finding an electron. And we should mention this too, that like in the middle, like where these axes all meet, that's the nucleus. So like in the middle of this orange little bubble is the nucleus. It's just that the nucleus is so teeny, teeny, tiny compared to the shape and size of the electron cloud that they're not even showing the nucleus in any of these pictures. But where those three axes intersect in the middle, that's the nucleus. But what I am going to do is put two dots in here. Dot, dot. You could do the same. I like to put two dots in there to show that there could be two electrons randomly moving within this orbital. Orbitals can hold a maximum of 2 electrons. They're constantly moving, so we don't know the exact position of the electrons, but this is just a region where I have a high probability of finding up to 2 electrons. Every energy level has an s orbital, but here's the difference. Let's say that's like the 1s orbital, and now I want to do the 2s. So 2 would just mean second energy level. S means spherical. Well, the 2s orbital is just a little bigger. But it's the same shape. I mean, it kind of goes back to this picture where here was the first energy level and the second energy level. And so in the second energy level, it's just a bigger region around the nucleus, but S still means spherical shape. Oh, so it's just a larger spherical region around the nucleus where, again, I have a chance of finding 2 electrons. So I could have one over here, I could have one over here. But if I had the world's most powerful camera, these electrons are always moving. And so they could be up on the top, on the bottom, on the sides. We don't know. But I have a good chance of finding 2 electrons. Can you guess what the 3s orbital would look like? If you guessed just a little bit bigger sphere, you would be right. The 3s is still a spherical region around the nucleus where I have a high probability of finding 2 electrons. It's just a little bit bigger. The third energy level is just a little bit farther from the nucleus. Cool. All right. So the first energy level has an s orbital. The second energy level has a little bigger s orbital. Then when you get to the second energy level and beyond, you will find what's called a p orbital. All the shells, or all energy levels, except the first, have 3 p orbitals. Now I wish it stood for something that started with a p, but they're really dumbbell shaped. Dumbbell just meaning that they have 2 lobes, so kind of like a dumbbell. If you're lifting it, it's got kind of like 2 lobes on the end. Kind of similar. So I'm picturing the nucleus is in the middle here. So let's do this in red. Like right in the middle there. That's where I'd find the nucleus. And so now these p orbitals are like 2 regions. It's like 2 lobes where I have a chance of finding up to 2 electrons. These p orbitals are a little bit bigger and they're a little bit higher in energy. So there's no such thing as a 1p. We would never have 1p. Sad face. Wah, wah. 1 meaning the first energy level, p meaning these dumbbell-shaped orbitals. The first energy level is just too small. It only has this s orbital, a little spherical region where you could find 2 electrons. You will not find p orbitals until the second energy level and beyond. They have to be a little bit bigger and a little higher in energy. Now there are 3 p orbitals. They're the exact same shape and they're the same energy level. The only difference is that they lie on a little different axes in space. So their orientation is just a little bit different. But you still have a chance of finding 2 electrons. So let's say these are like the 2p orbitals. So we say 2, meaning it's in the second energy level. P, showing us this dumbbell shape. And then sometimes you might see like an X, Y, Z, just showing the axes that the orbital is on. So this might be like the 2p on the x-axis. This is the 2p on the z. And maybe this is the 2p on the y-axis. All equal energy. I'm going to put that in here. Equal energy. Just a little different orientation in space. And there are 3 of them. Okay, so each orbital can still hold a maximum of 2 electrons, even though they're a little bigger and higher energy. So you could have 1 in each lobe. You could have top and bottom. But again, the electrons are free to move. And so it's possible that at any given point in time, maybe they're in the same lobe. Now, if they are, they're probably not going to stay there for long because electrons are negative and like charges repel. But it's possible. This is just describing a region where I have a high probability of finding up to 2 electrons. Now, what if somebody said, draw me a 3p orbital? So maybe we'd say, okay, how about a 3p on the z-axis? Well, 3 just means that it's in a higher energy level that's a little bit farther from the nucleus. And so if I could squish it in here, maybe it would just be like this. It would just be a little bit bigger, so that on average the electrons can be a little bit farther from the nucleus. But there would still only be a maximum of 2 electrons allowed in that orbital. It's just that these orbitals can occupy a little bit larger space. They've got more room to move. Sometimes I think of it as like apartments, where the 1s is like a really small studio apartment, like just a 1-room apartment. Well, a 2s is still a studio 1-room apartment. It's just a little bit larger square footage. Well, now when you get to like the p orbitals, maybe you got like a 2-bedroom apartment. And so, you know, if you've got a roommate, you and your roommate are probably in your own rooms for most of the time, but maybe you stop by and chit-chat, or you watch a movie or something, and so it's possible that the electrons could be in the same room. But most of the time they would be in their own rooms or their own lobes of the orbital. Isn't this so wild? They did not tell you this in your last science class. Okay, so orbital shapes get more complex as more electrons are added to a shell or an energy level. The first energy level only has the s. The second energy level has an s, and it has these p orbitals. But then when you get to the third energy level, that's the first time that you find d orbitals. Oh my gosh! So the d orbitals are these guys. These are d orbitals. These guys in purple are the d's. They're a little bit bigger and higher in energy. There are 5 of them. Most of them look kind of like a clover in that they have 4 lobes. Oh my lord. I might put that in there. There are 4 lobes. They're higher in energy. They're a little bit bigger. And they don't start until the 3rd energy level. So now, for example, there is no such thing as a 1d or a 2d. Sad face. These purple orbitals that have 4 lobes, these clover orbitals, they're just too big and they're too high in energy. They don't fit in the first or the second energy level. You won't find these d orbitals until the 3rd energy level. But when you find them, there will be 5 of them. They're all equal energy again. They're all equal energy. Cool. And they can hold 2 electrons. And so somewhere in these 4 lobes there would be 2 electrons. They could be across from each other, maybe they're up on the top, maybe they're on the bottom, maybe they're like kitty corner. One of the d orbitals is a little bit funky. It's kind of known as the donut orbital, where 2 of the lobes kind of join up and make a ring around the center. So instead of it really looking like 4 lobes, it's kind of like 2 lobes and a donut. But it's equal energy to all the other ones, and so maybe there's an electron up in one of the lobes and there's an electron in the donut, but they still hold a maximum of 2 electrons each. And so on. The next orbital is called an f orbital. The f orbitals have 8 lobes, and they're super crazy. And they're bigger than s's and d's, or p's, and so you won't find these until, you got it, the 4th energy level. So there is no such thing as a 1f. Well, that'd be weird. There's no such thing as a 2f or a 3f. These would all be sad faces. The f's are not found until the 4th energy level because they're super high in energy and they're just too big. But when you do find them, there will be 7. They have 8 lobes, but there's one of them that's like a double donut. And they can still all hold 2 electrons. And so who knows? I mean, somewhere in these lobes there would be 2 electrons each. I don't know where. Maybe they're both in the donuts. And so I think of these as like apartments. Like you could have the 1-bedroom studio, but they come in different amounts of square footage. So 1s is small, a 2s is a little bigger, and so on. You could have the 2-bedroom apartment, kind of like the p orbitals. These apartments are all being shared by 2 people, or 2 electrons. Then you've got like the d orbitals that are maybe like a 4-bedroom apartment, but it's really only shared by 2 people. So you've got lots of room to spread out. And then you've got like the penthouse, this giant f orbital, where there's lots of space for electrons. Now this model on the bottom is kind of trying to show that energy of these orbitals will increase, that eventually electrons will fill the orbitals low energy to high energy. So the lowest energy orbital is always going to be the s orbital, then we'll move to the p's, and then the d's, and then finally the f orbitals.